In this video, we're going to take another look at the idea of an activation energy, and we're going to use this very nice online diagram from the Dexter Perkins Mineralogy textbook, and it is showing the phase relationships for the so-called aluminosilicates, Al2SiO5, which comes in three flavors. There is kyanite, there is selimanite, and there is also andalusite. And as you can see from the diagrams, these different minerals are stable at different pressures and temperatures. So in terms of reading the phase diagram, let's take a look at a particular case. So let's say we have a pressure of 6 kilobars and a temperature of 500 degrees centigrade. So go ahead and pause the video for a second and tell me what the stable phase would be, Al2SiO5. Would it be kyanite, selimanite, or andalusite? So at this set of PT conditions, here's 6 kilobars there, 500 degrees is about there. So those conditions intersect here. They intersect in the kyanite field. So that means kyanite is stable. So let's consider the case of, let's say, selimanite transforming into kyanite. So let's say we had some selimanite in a metamorphic rock here, and it's being it's experiencing an increase in pressure and a decrease in temperature that forces it into the kyanite stability field. So how would we draw that? Well, we'll draw the axes of the potential energy diagram that we drew earlier. And so on the vertical axis is our potential energy. Reaction progress we'll call R, and that's increasing to the right. And let's put selimanite here and then kyanite over on the left. This is really rather arbitrary. Because kyanite has the lowest energy, it would be sitting here at some energy well, potential energy that is less than wherever selimanite would be situated. So let's put selimanite at some arbitrarily higher energy than kyanite over here. So there's some difference in potential energy. And eventually, selimanite would want to go into this lower energy state of kyanite, but it would have to get over this activation energy barrier, hence the term activation energy. So the magnitude of that hill, the height of that hill in terms of energy units, we can just call that E sub A, and that is the activation energy that must be put into selimanite to activate it. And we can even call the state over here an activated state that selimanite has to get into before it can finally make that descent into this lower energy well. When we talk about stable and unstable, there's another term that's very important. So here we have kyanite sitting at the lowest energy level, and that means that it is stable. But the way we've drawn this, a lot of diagrams are shown with kind of a flat area and then kind of a hump for the activation energy and another flat area. But the energy diagram doesn't always necessarily look like that. You can have an energy well where it's not so easy for something to climb out of. So the way we've drawn this here is there actually is this localized low energy system for selimanite. So let's clean up the diagram again and just redraw it so we can focus on the case of selimanite. So we have energy and then reaction progress, and we will have a potential energy curve here where selimanite is perched at a higher energy compared to kyanite. Not a very smooth curve, but it'll get the job done. So this local area here is something that we can refer to as a metastable state. This is very important. So this metastable state is an area of local low energy. It's not the lowest energy in this system. If selimanite can somehow find a way to make its way over that energy barrier, then it will happily transform into kyanite. But here, the way we've drawn this, we've drawn it very specifically to show that there can be a little minimum in this energy well, and that energy well can represent this metastable state. And that's very important because when we ask questions like, is a system at equilibrium, this is not an easy thing to answer. So is something at equilibrium? Well, it might be, Or it could be that a system is occupying a local energy minimum. And it could be that despite our best attempts to disturb that local energy minimum, that the energy barrier, the activation energy, is just too large to get the system to go into a global lowest energy. So for equilibrium, that would be a global minimum in energy. And then a local energy minimum would be our metastable state. And so one of the big issues when conducting experiments or looking at natural systems and asking, do we have equilibrium? We have to ask, are we sure we're looking at a global energy minimum? Or maybe the system is perched in a local energy minimum, and we're looking not at something that's unstable, that's very happily stable, but really metastable. So it's not necessarily going to automatically convert into something else. What would be an unstable system, to go back to our energy diagram, so E and R, we can have a system that looks like this. That would be our metastable state. We'll just call it M. This would be our stable state S. Maybe a system over here on its way rolling down the hill. That might be an example of our unstable state, something that is not obtaining any barrier as it moves from high energy to low energy. But these metastable states, they are a very important issue when looking at both natural and experimental systems.